In this video, I'll be explaining what the impulse momentum theorem is. Throughout the video, I'll focus on major details such as the physical phenomenon, where the physics kicks in, assumptions that are made, and an opportunity for those watching to practice some problems. So, first of all, the impulse momentum theorem states that the change in momentum of an object is equal to the impulse applied to said object. It actually originates from Newton's second law of motion, F equals ma. If we rewrite acceleration as the change in velocity over the change in time, we get this. Now let's multiply by the change in time to get this equation, and that is actually the theorem. F delta t equals m delta v, or J equals delta p. The physical phenomenon is actually seen constantly in the world. For example, in football, it is seen very clearly. An offensive player with the ball, when running, has momentum, a mass and a velocity. He or she is then approached by a defensive player who tackles the other one, thereby applying a force over a duration of time in order to stop the offensive player. Similar situations include vehicle collisions, where a car with mass and velocity hits a wall, another vehicle, and a force is applied over a duration of time. One physics concept of the impulse momentum theorem is elasticity, a property of collisions represented by the letter K, lowercase, not to be confused with capital K. Elasticity is also related to kinetic energy. I'll explain how they are related in a second. For now, I'm going to explain what two objects in a closed system do upon experiencing four types of elastic collisions. Here are the four types. First, we have superelastic, where objects bounce off. Elastic, where they repel as equally as they struck. Inelastic, where they stick together, but they can still be separated. And completely inelastic, where they are stuck together. Back to the kinetic energy and elasticity. This chart explains their connection. You can compare the initial and final kinetic energies to remember how the two objects interact. For example, let's look at inelastic collisions. This is like a car crash, where the initial kinetic energy, when the two cars come and crash, is higher than after the collision. Elasticity can also be solved for by using this equation. V2F minus V1F over V1I minus V2I. This is because elasticity is the ratio of the relative velocity between two objects after the collision to the relative velocity before the collision. Another physics concept is the relationship between variables. Force, time, velocity. These are the easiest to identify. For example, force and time, inversely related. So say, for example, a car wreck lasts long, then the force is minimized. And this is actually the reason why the front of cars crumple easily, to protect drivers. Likewise, force is directly related to velocity. Big F, big V. Imagine this in baseball. Hitting a baseball with a huge force causes it to have a higher velocity, travel faster. There are two major assumptions to this theorem. One is that momentum is conserved if no net force is applied. Two is that the system is isolated. You can apply the impulse momentum theorem to any situation where an object with mass and a velocity is subject to a force for a period of time. Football, pair tackles, car collisions, etc. You could also predict how much force an object experienced by comparing force with time, using the inverse relationships. A simple example is the egg drop example. When catching a falling egg, one would move their hands down in the direction the egg falls, even after catching it. So for example, if I was to drop an egg right now, I wouldn't just catch it like this, because it would break. The time duration is so small that the force is really great, breaks the egg. So instead, when the egg falls, I still do the motion as if it was falling. I'm increasing the time duration and also decreasing the force. Other fragile falling objects like babies that are free falling should be captured with similar care. There's also the force velocity or time velocity. That one's easy to understand. Imagine striking a baseball with a baseball bat. Players continue to swing after striking. The increase in force and time greatly increase the velocity of the ball. A more complex scenario involves two balls. One has about 5 times the mass of the other. Think about it as a tennis ball and a basketball. So stack both on top, like in the diagram, and let them fall. They'll both fall separately. But when the basketball hits the floor and rebounds while the tennis ball is still falling, there is a collision right there. The basketball loses its velocity, its momentum decreases, but the tennis ball gains that loss, momentum, conservation of momentum. The tennis ball will jump pretty high, and if the difference between the two objects' mass is greater, the small ball will actually bounce off even higher, like right here. I'll provide. I believe it was a couple of problems to practice the impulse momentum theorem.